percent yield was the other part of the video that I showed you guys. And percent yield is a calculation you can make that simply says, what is your percentage? It's like, what's your score on the reaction that you ran? And all it's saying is that you take your actual yield and you divide it by your theoretical yield. And then you multiply it times 100%. Now, percent yield is kind of like saying, okay, remember I gave you guys a hot dog example. In reality, we know that we can make 2 hot dogs because all I had was 2 wieners. But in reality, I dropped one on the floor or the dog came and ate one. So I only made 1 hot dog. So that's the actual yield. In lab settings, in sciences in general, what ends up happening, the experiment does not run perfectly unless you're just like a grade A scientist. It does not run perfectly. And so what ends up happening is you don't actually make all of the theoretical yield. You don't make all that you can actually make. So in the hot dog example, if I drop one of my wieners, I only end up making 1 hot dog. So for the actual yield, the question will say, okay, if you, I don't know what that noise is. If you made, it'll always give you this number, the actual yield. In this class, this number is always given to you. So sometimes you'll have 3 givens. And your 3 givens, you'd have to figure out which one is your actual yield. Your actual yield is always given to you. It's going to be a product. So the actual yield is always the product, the number they give you for the product. And then the theoretical yield, you have to calculate this. Unless the question just gives it to you, but most of the time you're gonna have to do the calculation. Just like we did the calculations on all the other ones, you gotta do the same thing to figure out the theoretical yield. And then once you get those 2 numbers, you just divide them. So let's just do one from the worksheet really quickly. Let's do number 3 from the worksheet, a good one. If we just look at this percent yield worksheet, this is on Brightspace as well under chapter 8. The very first one I think I did on the video. The very first one says, determine the percent yield for the reaction between sodium and excess oxygen. When it tells you it's excess oxygen, remember excess just means extra. So it's already telling you that the sodium is your limiting reactant. So you do not have to do a calculation with the limiting reactant. You know, you don't have to figure out which one's the limiting reactant. It's already telling you that the 3.74 grams of sodium is the limiting reactant, and you have to figure out how much sodium peroxide you can make. It's telling you here that this number is the actual yield. But for other questions, you see you only had 2 numbers given in this question. For other questions like number 2 or even number 3, I'm going to skip down to number 3, you see you have 3 different numbers. These 3 numbers, you have this 82.4 grams, this 11.6 grams, and the 39.7 grams. It's saying that 2 of those numbers are reactants, and you have to figure out which one's the limiting reactant, just like we did on the other worksheet. And that 3rd number is your actual yield. So let's read through this one together to see if we can figure it out. So it says, determine the percent yield for the reaction between 82.4 grams of rubidium and 11.6 grams of oxygen gas if 39.7 grams of rubidium oxide is produced. So this word is produced. It's telling you that this is the actual yield. So remember, and just means you're gonna draw a plus sign there. So if I go out to write this reaction, I'm saying I have rubidium and oxygen gas produce rubidium oxide. It tells me how much of each one I have. It says I start off with 82.4 grams of rubidium, 11.6 grams of oxygen gas, and I produce 39.7 grams of the rubidium oxide. So in this case, this is my first A, this is my other A, this is still gonna be my B. I have to figure out which one of these two reactants is gonna give me the least amount of B. Once I figure that number out, that least amount of B is my theoretical yield. I already know my actual yield because this is my actual yield. Are you guys following me so far?
Yes.
One question.
All right, go ahead, Pawan.
Need to balance here or no?
Yeah, we definitely have to balance it. Thanks for the reminder. We definitely have to balance it. So let's go ahead and balance that right quickly. It's saying what if I balance it?
4, 1, 2.
4, 1, 2. Looks good to me. All right, so if I work this out, I'm gonna work it out just like I did the other limiting reactants. I gotta set up two calculations. The first calculation says I start off with 82.4 grams of rubidium. And then the second calculation is gonna say I start off with 11.6 grams of oxygen gas. All right, so let's go through this pretty quickly. You guys help me do some of these calculations because I don't have them all calculated out. The first step, since I'm in grams, is I need to convert to moles of rubidium. So 1 mole of rubidium, if I look at the periodic table, it's in column 1, is 85.47.
I have 84. Is that okay? 84.46.
On your periodic table?
Yes.
That's interesting. Maybe, let's see. Actually, never look at rubidium.
I have 85.47.
I think your periodic table is just a little off. It should say 85.47.
Okay.
All right, so that's my first step. Second step says the mole to mole ratio. What's the mole to mole ratio, guys?
2 to 4.
2 rubidium oxides to 4 rubidiums. And then the last step says the molar mass of rubidium oxide. So somebody calculate that for me and see if we get the same answer. And I want to point out why you guys do that calculation is that, remember, typically, if we're trying to find the limiting reactant, we can typically just stop here at moles. The main reason we're going to grams is because I still have to find the percent yield. The percent yield is going to say my percentage, my actual yield over my theoretical yield. And this is going to be in grams, and this is in grams. So both of these numbers need to be in grams. And while you guys find the molar mass of that, I'll go to this setup. 1 mole of O2 gives me 32 grams of O2.
So I have one question. For the second parentheses, you're always putting the product there, right? Basically?
Yeah, at the top. Yep, you always put the product at the top. Or
Okay.
whatever you're looking for. So in these questions, we're looking for the product. Some of the other questions that I gave you, like on Monday, you weren't necessarily looking for the product. You were looking for the other reactant. So it just depends on what your B is.
Okay.
So whatever the question's asking you for is what I'm getting at.
Okay.
Mm-hmm. Mm-hmm.
Okay.
Anybody have a molar mass for rubidium oxide?
90. I got 90.11 grams.
90.11, anybody can second that?
Is there 4 or 3 sig figs?
Let's,
Oh, sorry.
I'm not saying the answer, I'm just saying the molar mass for RB2. Oh,
Oh, 186.94.
Oh, okay.
186.94?
Yeah.
Yes.
That sounds good, 186.94.
So we didn't do for rubidium, right? We just did 2 to get the molar mass.
Yep, 2 times RB plus 1 times O.
Okay. Okay.
All right, so then when we get to the oxygen one, what's the ratio from rubidium oxide to oxygen now?
2 to 1.
Okay, so 2 rubidium oxides to 1 oxygen gas. And then the last step is going to be the same because it's just the molar mass of rubidium oxide. And we already calculated that. And then we just need to put these in our calculator and see which one gives us the least amount. Anybody got a number for the first one?
$90.1 gram.
90.1 grams.
90.1 gram.
Okay, what about for the second one?
271.
Say it again.
271.
271 for the second one?
Yeah,
Okay.
that's what I got.
I got something a little different. Let's see. Anybody else get anything?
35.53.
135.
Yeah, 135 is
45.
135.
136.
3 sig figs, so we can just say 136. I'm
136.
not gonna round it to the end just yet, guys, just because I still gotta do another calculation. So either way, which one's the least amount? Or which one's my theoretical yield?
The first
RB.
one, ribbon.
Yep, so we're saying this is the theoretical yield. So to calculate the percent yield, all we have to say is the actual yield, which is given to us, divided by the theoretical yield, which we calculated. And we're saying the actual yield, what is it off the paper? 39.7
Mhm.
grams of the rubidium oxide divided by 90.1 grams of the rubidium oxide. So this is percent yield times 100%. When we divide those two numbers, 39.7 divided by 90,
44.1%.
you said 44?
Mm-hmm.
All right,
Yeah.
yep, 44.1% sounds good to me. We need 3 sig figs, yep, 44.1%. That's our percent yield. Now, remember I said this chapter is the toughest chapter in our book. It's mainly because we got to do a lot of calculations, not because it's so tough.
Can
Okay.
I ask a question about like 5?
Okay.
Okay, so when it says like the unknown amount of CO,
Okay.
so basically we have a couple of questions on the other side that talk about the unknown.
Okay, that's fine. Let's talk through this one really quickly. I'm just gonna, all it's saying is we still got to determine the percent yield. It's saying we're starting off with this antimony oxide that looks like this. And then it says, and excess carbon. And then it says, produces antimony along with an unknown amount of CO. That's all it's saying. So it tells us how much antimony it produces. So in that case, the 17.3 grams is our actual yield. We don't even really have to pay attention to the carbon monoxide. We only need it to properly balance the equation. So this is just like question number 3, where they give us the actual yield. It says we start off with 28.1 grams of the antimony oxide and then 17.3 grams of the carbon. And then we have to figure out which one of these reactants are limiting reactant, figure out how much of it it's gonna theoretically make, and then we divide those two numbers. Does that make sense, Malika?
I think so.
Okay, so unknown amount.
Wait, what happened?
In this question, basically the CO is not really changing anything in how we relate to the
Yeah,
mathematics.
except to balance the equation properly.
Okay.
Yeah, so it doesn't do anything else with the other calculations. I'm just looking at number 5, just showing you guys that this is just helping you write a balanced equation. It's telling you what your reactants are and what your products are. So if it's giving you 3 numbers, 2 of them are for the limiting reactant, the other one is the actual yield. All right. So that's my recap of yesterday's lecture. It took longer than I thought, but that's fine. It's 2 o'clock, so let's just go ahead and take a break. And while you guys take a break, I'll try to figure out how to unhydrate. And then I'm going to keep going with the lecture. I would like to start chapter 9 today so that we can finish it up for tomorrow. Do I have any questions before we take a break? All right, so it's 2:05. Let's come back. You guys want to come back in 15 minutes? So 2:20.
Sounds good.
Good.
All right, see you in a second.
Okay.
Confusion balancing question number 4.
So to wrap up chapter 8, I want to talk about the enthalpy of reaction. All right, enthalpy of reaction. What this is, first of all, the way we draw the sign for this is we say it's the triangle H, and then RXN stands for reaction. This H stands for enthalpy. And remember that this triangle is always going to be the difference, the final minus the initial. In our case, when we talk about chemical reactions, it's going to be the products minus the reactants. But we call this the change in enthalpy of a reaction. So all this statement really means is as the amount of thermal energy, and remember all thermal energy really is, it's just heat that is emitted or absorbed when a reaction occurs at constant pressure. So when we have this, it's basically saying that when we run a chemical reaction, how much heat is either given off or being absorbed by that reaction. So some reactions, like combustion reactions, Remember, combustion reactions take a carbon and hydrogen compound. And in the presence of oxygen gas, it's always going to produce carbon dioxide and water. So this is a combustion reaction of methane gas. In combustion reactions, they always emit heat, meaning they always give off heat. It's like an explosion. It's always going to give off heat. And we say that that's an exothermic reaction. Just to remind you guys, exothermic means we emit heat. And endothermic means we absorb heat, or the reaction absorbs heat. So when you have a combustion reaction, they're always exothermic. They're always going to give off or emit some heat. And basically, the change in enthalpy of this reaction just tells you how much heat it's going to emit. So this number, this change in enthalpy of this combustion reaction of methane, it's given to us by this symbol right here. And this is a number that's going to be given to us, negative 802.3 kilojoules. So the way you'd see it is that you'd have your balanced chemical equation, and then to the right of it, you'd see this change in H reaction equals negative 802.3. This number is given to you. And there's tables on the internet and in the back of the book that can give you this number. So it's called the change in enthalpy of a reaction. It just tells us how much heat is going to be given off of from a reaction, or how much heat is being absorbed in a reaction. Remember, all these reactions take energy, and they're either giving off energy or they're absorbing energy. Now, when we talk about these reactions and when we relate it to the amount of energy that it gives off, we can set up similarly a mole-to-mole ratio between the amount of heat and the amount of moles of each substance. So just like before, you know, we said 1 mole of methane for every 2 moles of oxygen, for every 1 mole of carbon dioxide gives us 2 moles of water. We know these moles to mole ratios because we're just looking at the coefficients out in front of each substance. We're going to continue to look at these coefficients because this is how we're going to relate it to the amount of heat as well. But instead of saying 1 to 2 for methane to oxygen, I'm just going to say 1 methane gives us 802.3 kilojoules of heat. 2 moles of oxygen gives us 802 kilojoules of heat. 1 mole of carbon dioxide is going to give us this much heat, and 2 moles of water is going to give us this much heat. So we're still using the coefficients out in front of each substance. We're just now relating it to the amount of heat that's going to be emitted or absorbed. And remember, the negative sign just means it's emitted. The positive sign means it's absorbed. So we can set up similar ratios, saying 1 mole of CH4 is going to give us negative 802.3 kilojoules of heat. Or we can write it vice versa. Negative 802.3 kilojoules of heat gives us 1 mole of methane. We can say the same thing for 2 moles of oxygen gas. 2 moles of oxygen is going to give off 802.3 kilojoules of heat, and vice versa. We can write it this way. And I should put O2 so it's clear. All right, so we can set up calculations using these same ratios, but now we're just converting the ratio to the amount of heat. We can set up calculations to decide how much heat we get from any chemical reaction depending on how much starting material we start off with. So let's do an example. Let me get a new page to start an example. All right, my example says, if I have an LP gas tank. In a home barbecue. You guys, LP stands for liquid petroleum, not Leah Page. All right, so liquid petroleum, it's saying I have an LP gas tank and a home barbecue. Just think about the barbecue, a gas barbecue grill. It contains 1.8 times 10 to the power 4 grams of propane. And propane is C3H8. That's the gas that's in those little gas tanks that you can get from Home Depot when you want to buy a gas tank to do like a boil or if you have a home barbecue. And the question says, calculate the heat in kilojoules associated with the complete combustion of all of the propane in the tank. All right, so then the question gives us this reaction that says the combustion reaction for propane gas is C3H8 plus oxygen gas is always going to give us carbon dioxide plus water. And if balanced properly, it looks like 5, 3, 4. And then on the side, it says the change in enthalpy of this reaction is equal to negative 2,044 kilojoules. Like I said, this change in enthalpy of the reaction is always given to you. You're gonna have the equation, the balanced equation, and then it's gonna say on the side, the change in enthalpy of this reaction is that much. So this number literally means when this reaction is completely run, this amount of heat is given off. Remember, the negative sign just means it's released, and this is how much energy is given off. So let's say I'm going to go barbecue for the weekend. I start off with this amount of propane gas. So this is my given, this 1.8 times 10 to the power 4 grams of propane gas. And I want to know how much heat I'm going to burn off starting with this amount of propane gas. Now, I just told you guys we can set up a relationship between each substance and the amount of heat that's given off. So 1 mole of propane, once completely reacting, is going to give off this much heat. So if I have the grams of propane, what do you guys think my first step is to do? And what's always our first step?
Change it to moles.
Change it to moles. Our first step is to always get to moles if we're not already in moles. So in this case, how do I go from grams to moles? Just like every other time.
1 mole of
1 mole of propane is going to be equal to the molar mass of propane. So we're saying 12 times 3 plus 8 times 1. That's 36 plus 8, 44. Let's say 44.3 and 11, 8 is 11. So something like 44.11 grams of propane. So now that I have it in moles of propane, the next step to calculate the amount of heat, I can set up a ratio between the propane and the amount of heat by simply saying
Sir,
one,
I'm confused here.
well, let me finish.
44 or 56?
12 times 3 is 36, right? And then plus 8, 36 plus 8 is 44.
Thank you.
Maybe you did 12 times 4. All right, so then once we get to moles of propane, we can set up a ratio that says one of these gives me this much heat. So I can say 1 mole of propane is going to give me or give off this much heat. And I simply put this in my calculator and I come up with an answer. So 1.8 E4, 1 divided by 44.11, and then 2044 divided by 1. All right, so I need 2 sig figs in my answer. And with 2 sig figs in my answer, I end up getting 8.3, here, I'll write it down here, 8.3 times 10 to the power of 5, or I can say 834,000, I'm sorry, 830,000 kilojoules of heat.
So you don't put the negative in there, that negative 2044?
You can put you put the negative in there and the answer should be negative. And this essentially means, remember that negative sign doesn't really mean you have a negative amount of heat. It just tells you which direction your heat is flowing. So in this case, your heat is flowing outward, and in all combustion reactions, you can feel the heat because it gives the heat off. So just think about, you have a gas tank outside, you're burning it. It starts off with this many grams inside the gas tank of propane. And after you burn all that gas off, this is how much heat you're giving off or how much energy you're giving off. Does that make sense? Okay, so let's see if we can do another one. You guys set it up. These problems, I think, are pretty straightforward, but because I don't have a worksheet on this, I don't know if it's because I don't have a worksheet on it or because I go over it really quickly. When it comes to quizzes and tests, you guys seem to get these problems wrong. And it's the same thing with the stoichiometry. We're always going to go to moles first. Once we get to moles, we can convert our moles to heat just by saying the same ratios, but this time relating it to the amount of heat. So let's do another example just so I can give you plenty of examples for this one. Let's say my next example says I have octane, which has the formula C8H18. And that's like the octane. Okay, and our gasoline burns according to the equation. And the equation says 2C8H18 plus 25O2 gives us 16 CO2 plus 18 H2O. And the change in enthalpy of this reaction is negative 5,074.1 kilojoules. It's just a male. All right, the question says, what mass of octane in grams is required to produce 1.55 times 10 to the power of 3 kilojoules of heat. Now this question is kind of backwards, and I'm giving it to you just so you can see the different ways the questions can be asked. This question's saying, okay, I have my answer. Now, how much octane did I start off with? So in this case, it gave me the amount of gas that I have, and it asked me to calculate the heat. In this question, it's giving me the amount of heat, and it's asking me to calculate how much gas did I start off with. So, can anyone tell me what a first step would be? If this number, if kilojoules is my given, what would be the first step? And what's always the first step?
Convert to moles.
Convert to moles. So yeah, we get to convert to moles, but how do we convert to moles in this case? Does anyone know?
Give me a second.
Okay, just look at the previous example.
Do we convert?
We still use the molar mass.
Well, not quite the molar mass because we're starting off with kilojoules. So using the molar mass.
We need to convert the kilojoules to grams?
No, not grams. We got to convert to moles first. The first step is to go from kilojoules to moles, but how do we relate this kilojoules to moles?
Mole ratio?
Yeah, just the ratio. So we're saying, okay, we're looking at octane. The ratio of this amount of heat to moles is saying for every 2 moles of octane, I get this much heat. So if I want to convert this to moles, I'd start off by saying, if I have this much heat, well, I don't even have to say, I could just say the positive version of it. 4.1 kilojoules. I still want to convert it to moles. So now it's saying 2 moles of octane is going to give me this much heat. Sorry, I wrote down the wrong number right here, guys. Here, let me write it on a separate sheet. Ignore this. My given is this 1.55 times 10 to the power of 3 kilojoules. If I want to convert this number to moles, the ratio is this much heat for 2 moles of C8H18. So I can say 2 moles of C8H18 gives me this much heat. This should be a 4.1 kilojoules like that. All right, so that's my first step. I'm just trying to get to moles. In this case, I use the ratio from here to here to get to moles. Once I get to moles.
Why don't you put a negative next to it, the kilojoules?
Because it's asking us to find the grams. And remember that negative number, that negative sign is just telling us which way it's going. And we're not gonna get a negative amount of grams is what I'm saying.
Okay.
So we just know that even if you put the negative sign there, it's gonna give you a negative amount of grams, and that doesn't exist. So I just put it there. I didn't put it there just to like not confuse you guys. All right, so when we do this, the next step, can anyone tell me what you think the next step is? Because now we're out of kilojoules. and we're into moles, and the question's saying, what's the mass of octane? So if I'm in moles of octane, how to go from moles of octane to grams of octane?
Find
Then
the
we
molar-
use the molar mass.
Then we use the molar mass that says 1 mole of octane is gonna be whatever the mass of octane is. So 8 times 12, 96 plus 18, I don't know. All right, so I end up getting 114,
Yeah.
26 or so grams of C8H18. And then that's how we end up getting our answer. All right, so we put this in our calculator. And I ended up getting 69 point, and I need 3 sig figs, so 69.8 grams of propane. So the main point is to realize that this equation, whether we're talking about propane, whether we're talking about oxygen, carbon dioxide, or water, we're just using the coefficients out in front. We're using these coefficients that say, okay, if every 25 oxygens, I get this much heat. For every 16 carbon dioxides, I get this much heat. For every 18 waters, I get this much heat from this balanced chemical equation or chemical reaction. All right, let's see if we can do one more and you guys try to figure it out yourselves. Do I have any questions before I keep going? All right, so let's keep going. How much heat is produced when 0.085 kilograms of sulfur reacts according to the reaction below. So the reaction says I have sulfur plus oxygen gas reacts to form sulfur trioxide, and the change in enthalpy of this reaction is negative 792 kilojoules. So you guys spend a second and see if you guys can work this out. Okay, does anyone know where to start? Can anyone give me a starting spot? If I have
1 mole of sulfur equals to 32.06 gram of SO3.
Okay, but we got to remember, we're starting off in kilograms in this case. So we're
kg.
0.085 kilograms. What do we have to first do? We definitely need to convert it to moles, but we know how to convert grams to moles. So we got to convert it to grams first. Some of us can look at this and say, oh, let's just move the decimal spot place over 3 spaces. And if you can't look at that, you know, the first step would be 1 kilogram equals 10 to the power of 3 grams. All right, so then the real first step is to get to moles. So yes, Puan, what's the molar mass of sulfur? 1 mole of sulfur equals
32.06.
32.06, that works for me, or 32.07. Let's do 32.07 grams of sulfur. So then what's my next step, guys?
2 moles of sulfur equals to 2 moles of SO3.
It would be the
oh,
the
okay.
heat that's given off.
Yep.
The
So,
two.
Jaleesa, I think that's you talking, but let me correct Pawan right quickly. Pawan, typically, if we're trying to go from sulfur to sulfur trioxide, yes, its ratio is 2 to 2. But in this case, we don't care about the product. We're just relating this 2 to this amount of heat. So all we have to say is for every 2 moles of sulfur, we're going to give off this much heat. So you don't have to do that 2 to 2, although you still get the same answer just because you're multiplying it times 1 essentially. But let's say this number wasn't 2, you'd get a different answer. So just remember, you don't even have to figure out the product in this case. It's saying once this 2 moles of sulfur react completely, it's going to give off this much heat. So
Okay.
what'd you guys get with 2 sig figs in your answer? All right, so we need 2 sig figs. With 2 sig figs, I end up getting negative, what, 1.0 times 10 to the power of 3 kilojoules. All right. That's pretty much how we figure out how much heat is given out for any reaction. So like, let's just imagine we're cooking on the stove. We can calculate how much heat is given off if we know how much gas we start off with. Same thing with the barbecue outside. If you have a gas grill, if we know how much of the gas we're starting off with, we can calculate how much heat is given off from this reaction. So this wraps up chapter 8, guys. This is all that we have to know from chapter 8. Remember, all we're doing is relating one substance to another. In the terms of enthalpy, we're relating the amount of heat to the chemical reaction. And we're still just setting up a similar like mole to mole ratio, but this time it's like moles to kilojoules. You know, 3 oxygens for every this much heat, 2 sulfur trioxides for this much heat. So that wraps up chapter 8.
Can I ask a quick question?
Yeah.
On the homework assignment, when we have, one of the questions has us, it's asking about kilograms and milligrams. So we're going to need to convert those over to grams also, right?
Yeah, yeah. So to use the molar mass, we always got to have grams first.
Okay.
If it's in milligrams or kilograms, it's a matter of you flipping the decimal place over 3 spaces.
Both of them?
Yep, so one goes 3 spaces one way and milligrams goes 3 spaces the other way.
Ah, okay.
So if I started off, let's say this number was 0.085 milligrams and I wanted to convert it to grams, you know, I'd go 1, 2, 3 and put some zeros there.
Okay.
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 So, or I could just set up the conversion that says 0.085 milligrams, and I'd say 1 milligram equals 10 to the minus 3 grams. That's the only difference. One's positive 3, the other one's negative 3.
1 kilogram.